some applications, even combination could be interesting. Yeah.
Okay.
So
Yeah, once you go PFAS free, there is a range, you know, various options in terms of chemistry, what you can do. Let me just go quickly and grab my power supply, because I think maybe
Sabia, I assume we have different time zones of the people listening. Probably
yes.
from early morning till late in the night already. Yeah. It's always quite interesting in this online meetings.
So most of us, I mean, most of the listeners are in US, and me and the speakers, you and Luka, are from Europe. So I don't know, I would say maybe there are some Asians as well here. So I have no idea. But I know there are almost 95 registrations. So yeah.
Hi, this is Josie Cranville. I'm one of the staff members supporting. We actually now have 150 registrants. A bunch came in last night.
Yeah. So, Luka, we have to deliver something interesting.
Yes, you both have to deliver, I would say. So.
Don't tell me, I'm getting more and more nervous.
No, it's great. But West Coast, I guess it's now 7 in the morning or so. Yeah, this is so.
Yes.
Welcome to all those having first coffee.
Just checking.
Well, good morning, folks.
Morning, Nelson.
Hello.
Morning.
Morning.
Good morning, Nelson.
Greetings. Hello, Ram, Mike.
Hi, Nelson. Good to see you. Abhi, I think it's time.
Sabi, you're muted.
Hi, guys. Can you hear me?
Yes.
Perfect.
Yes.
So, Maria, shall we already start now? Because I see quite a lot of people are missing. We have almost 150 participants now.
It's normal to have like three quarters of the people who registered to actually show up. So this is not
Okay.
bad. We have 70 right now, and a couple more people are coming. It's up to you, sir.
Okay, so let's
go.
start because we also have the fact that we have some difference in time where people are and the speakers. So again, let me start. My name is Sabia Gan. I'm the chair of the interest group Chemical Applications. And I have been tasked to organize meetings where we talk about or we speak about interesting topics in the community. Last year, we started this discussion on PFAS, where we had two speakers speaking on the topic more related to the regulations, one from Europe, and there was a person from EPA in US who spoke about the US aspect of these PFAS. And then I was thinking about a new topic, I would say, for this year, and I thought, why not just continue the discussion on this topic, which is very, very, very important as the regulations are changing, and we are really encountering a lot of, I would say, technological changes and challenges in PFAS. So going forward, just the house rules. This presentation, this meeting is recorded. So if you do not want to be recorded, so mute your video. If you have questions, you may ask questions by typing your question in the chat box, or you could raise your hand, and I will make sure that you have you can ask questions. So in the way it would work is the speaker would speak for 30 minutes, and then we will have 10 minutes to 15 minutes of questions later on. Going forward, just to let you guys know that this meeting is recorded, and for people who are or the members who have not had chance to listen to this presentation, they can actually view the recorded presentations in the AATCC communities, and you will have to go down to the chemical interest group, and you will find the recording right there, I would say. You can also invite your colleagues to listen. Without ado, we have two speakers today, and they were very kind enough to accept the invitation. The first speaker is going to be Dr. Hegemann. He's actually my colleague here at Empa. He's the head of plasma and processes in the lab of advanced fibers. He has a degree in physics, and he did his PhD in material science. And I believe since 2006 or so, he has been group leader at Empa. He's going to talk mostly about the basics of PFAS refloatment, and also speak about what Empa is doing in developing PFAS alternatives or technologies which could replace PFAS, current PFAS. And then our second speaker is more from industry. He's Dr. Luka Kovacevic. It comes from Rudolf Chemie. Probably a lot of you already know this company. It's a company in Germany, so he will speak more about it. And he will talk more about the industrial aspect of PFAS replacement, giving us some examples of how they try to answer or provide solutions in form of bionic finishes. Lukas is actually has a PhD in chemistry, and yeah, looking forward to this talk. So without ado, I would have Dr. Hegemann speak first. We have 30 minutes of presentation and around 10 to 15 minutes of questions. So Dirk, the floor is all yours. I'll stop sharing now.
Thanks, Sabia, for this really nice introduction. I will just get my presentation running. Pointer, there we are. So welcome everyone. If it's early morning or already later that day, I really appreciate your interest in discussing options, but also limitations to replace PFAS. Just briefly, Empa is a research institute in Switzerland. We have these 3 sites, and we are here more in the eastern part of Switzerland in St. Gallen, where we deal with functional materials, the life sciences, and this is also including the textiles. PFAS is not a local issue. Yeah, it's globally, you find them probably meanwhile everywhere. When you look at the 5 Great Lakes in Northern America, you find everywhere different kind of fluorocarbon materials. Still interesting to mention, there where the population density is higher, you see a higher precipitation and also density of PFAS in the water. And what's also interesting is that the recent precipitation is mainly based on shorter chain PFAS, so that might indeed be a result of the larger chain PFAS meanwhile are banned. But still, all kind of different of these long chain you still find in the lake. So it's indeed an ongoing issue. And meanwhile, I guess it's also accepted that PFAS is linked to a negative health outcome. And one major industry responsible for the, let's say, accumulation of PFAS in the environment is indeed textile industry. Yeah, if you compare the amount, these are data for Europe to other fields, so it's quite substantial, the amount of PFAS that are used, and a lot of them as fluorosurfactants, so that means textile finishings, and exactly this is what's causing the issues, because it's worn, it's abraded, and it's introduced into water after laundering and so on. So this is the issue, but why PFAS are still in use? If you look at the video, you might know the answer. Yes, they are oil stain repellent. They have extremely good effects. How can they be replaced? I like to consider what plasma technology might contribute, since we are working with it. Are there other alternatives? Actually, what we have done here was in 2005. As Sabia mentioned, I was not long time with Empa, and at that time we were using PFAS, but we replaced the common PFAS that was typically 1 micron of C8 chemistry by a different kind of chemistry, only 300 nanometer thick. So we were always aiming in lowering the amount of fluorocarbons used, and we will see later tendencies, yeah, they go in a different direction. Anyway, now let's look more at the fundamentals. What makes PFAS so special? Yeah, it has lowest surface energy and able to repel not only water, alcohol, oil, blood, stain, and so on. You compare different substances, you realize the highest non-polarity you have with terminal CF3 groups, and therefore that has the main interest in PFAS to use these. It could not, the amount of fluorine cannot simply be reduced, at least by introducing some hydrocarbons, because then you might also get the polar component, and they are by far not as good. So by far the best treatment you get is a mixture of CF3, CF2 groups, and that is what is PFAS all about. Another aspect, not only surface energy, is that when you compare PTFE to polyethylene, it's a higher density, lower density. But when you look at the volume occupied by a unit, so the CF3 group, or here in this case the CF2 group, it occupies a much larger volume than corresponding CH2 group. And in literature, this is known as fatness. Yeah? So that the fluorocarbon functional groups contain a lot of space. And that adds to the important aspects or characteristics of PFAS. You can do some studies with an ideal self-assembled monolayer, where you only have then here's the chains of CF2 groups, terminal CF3 groups. And they indeed have quite some space among each other, even when they are tightly packed on a surface. And that adds to the effect that you have a very low interacting surface area, and that repels not only water, but all other liquids and stain as well, since all these can contain their shape and their repelled. That would be the ideal situation that would tell you, a few nanometers should be sufficient to reach these extremely good effects. The reality is a little bit different. If you want to do self-assembled monolayers, you always have defects where water can interact, since these are fluorosurfactants, so that means you need a reactive group to fix them on a surface, which is typically polar. Water can penetrate and even accumulate at the interface. And for this reason, the effect is better when you have longer seed chains on one hand and thicker films of fluorocarbons. So that is the reason why these micrometer thick chemical coatings are typically used. you are well aware, mainly these fluorosurfactants with these functional groups. And the long chain, they are meanwhile banned in most regions, most industrial fields as well, since they are persistent, bioaccumulative, and also toxic related to the health issues they might cause. What has been done? They're replaced by C6, but if you look at the chemistry, they are still fluorosurfactants, so you don't win that much. And if you remember the very latest results from the measurements, what you find in the Great Lakes, you find still the long chain, but now you also find all the shorter chains related to the replacement with the shorter chain chemistry. So that doesn't help a lot. You get almost comparable results. However, larger quantities have to be used. Yeah. So it's not really a situation you like to have. You replace one PFAS with other PFAS and do even need more of them to get comparable results. So a restriction prohibition procedure is underway. Let's see, but there might be delays. Let's see where it's going. The only chance is avoiding PFAS. So C0 chemistry. We will have the next speaker going more into detail. The idea is to get, of course, also a high durability. And question is, can durability be enhanced? Might lower quantities be used? And is it really only the methyl group CH3 or methylene CH2 groups that can replace the, let's say, similar CF3, CF2 groups? Again, let's check some surface energies. Here are the fluorocarbon containing. And if you look into table of element below fluorine, there's chlorine, bromine, iodine. Yeah, that might be a replacement. But when you look at the surface energies of a similar substance, they tend to increase. Okay, you might also not like to have too much chlorine bromine as a textile finishing, but anyway, that doesn't seem to be a way. What looks more promising is when methyl groups are bonded to silicon or silicon oxides or siloxanes. There you also have low surface energies, and the lowest when you have a high number of methyl groups bond to silicon. So these silanes, siloxanes might indeed be the best selection to check their potential to replace PFAS. And when you look at literature here, patent literature, indeed, meanwhile, you find plenty of activities, and some they are also claim very good oil repellency, using a kind of a hierarchical structure. Many of these SiCH3 groups decorated bond to siloxane, and this is the R group here that fixed to this hierarchical structure of, let's say, a siloxane chemistry. That is a viable approach. However, now you might need 10 to 40 micrometers, so no longer 1 micrometer C8, or even less if you do it properly. Now you're in the range of tens of micrometer you need to apply on a textile. You know it's changing the fabricant, other maybe even pressability and other properties. And you should be aware that the siloxane, they are not out of discussion totally. Yeah? They are, meanwhile, mainly these cyclic siloxane, they are also discussed if they should be banned, because they also persistent and accumulate in the environment. And at least for the cyclic, it seems to be proven that they can also cause health issues. Not yet that clear for the linear, it will be still followed up. And if you apply siloxane chemistry, you should make sure that you're not leaching these kind of substances. They are leached from cosmetic products, and therefore they are now under consideration. Good. Okay, now let's look what we might do with plasma technology. So, of course, we can also use these small molecules of siloxane, bring them into the plasma. Plasma is a reactive ionized gas where you activate your monomer depending on the energy you have. And those activated molecules then diffuse to the surface, and surface engineering can also be done by supplying energy. And finally, you have a deposit, so you grow what we name a plasma polymer film. That is different than wet chemical approaches, since it's indeed growing layer by layer. It gets cross-linked. It can give a very good adhesion on different kinds of substrate material, and due to the cross-linking, you get a high durability. The interesting aspect is you have hot electrons that supply the energy in the plasma, but the gas temperature stays close to room temperature. Nevertheless, you have energies on the order of tens of eV, both in the gas phase as at the surface. Finally, to do chemistry, and this is dry chemistry at room temperature, so from the vapor phase. So that are just in a nutshell the advantage of using the plasma. That has been applied in different fields, not only hydrophobic coatings, can be also adhesion promoting, hydrophilic coatings. We have pilot scale reactors at Empa. We do upscaling. We do transfer to industry. Just a few examples from the textile field. Surgical sutures, their enzymes, vitamins can be attached, blood filtration can be enhanced, tissue engineering, or you do composite materials where you don't need a primer, you just apply a nanometer thick plasma polymer film that promotes adhesion. So everything is done at the nanoscale. We are in the nanometer range. Look into more detail, taking this hexamethyl disiloxane as a model molecule that can enter the plasma. And typically, as soon as it enters the plasma, it gets already vibrationally excited. So very low energies are sufficient to break bonds, to do chemistry, as mentioned, in dry conditions close to room temperature. And then you might have different branches of reaction pathway, and you can look what might be the energy to get those film-forming species. In this example, it's around 14 eV, and this is a key parameter because now you can use this energy and apply it in a controlled way to your plasma process, plotted here on the scale, and then you can, for example, measure the water contact angle, so the water repellent properties, and the density, and density tells you something about cross-linking. And when you supply energy just a little bit above this 14 eV, you still have very good water repellent properties, but here you see now you can already increase density, that means cross-linking, and you get very high durability. This can be applied on scaffolds, on textiles, and here you see its advantages to do this at low pressure, LP compared to atmospheric pressure, because in low pressure you have a better penetration of those plasma activated species into a complex 3D shaped structure. And that can be further shown if you look at the surface that is directly exposed to the plasma or shielded from the plasma, so that you have only diffusion contributing to your film growth. You can realize that on one hand, you get a better penetration as you might expect. So typically, if you have just one reactive species, you might expect an exponential decay, but it's more like a linear decay. So you have a good penetration, and on top, you see that even underneath the shielding, you have a high contribution of these SiCH3 bonds and therefore highly hydrophobic properties. Diffusion coefficients, they go 1 over P, so that's 1 over the pressure, and that's the reason that this works much better at low pressure. And on top, if you select the chemistry right, it can be this molecule, meanwhile we are also using other molecules, but you can create a situation where you form different kind of reactive species with different reactivities. You have, for example, one highly reactive radical that deposits here more on the top and or just at the, let's say, inlet into a structure. And then you can also create less reactive species and they diffuse much further into the textile structure. And this way you can optimize the penetration into a textile structure and thus also the hydrophobization of fibrous materials. That has indeed been optimized over recent years. We do this directly on the fiber, on yarn material, because this way we get the best, let's say, treatment on every filament. So we wrap every filament with a very thin siloxane film. We do this at high speed. Can also be transferred to industry. That is the next we are doing. And just to show the difference, the plasma coated, it's a knitwear, so it's an open structure. It takes up water. This is here just the colored water, but then it shows quick drying properties, while a reference then sucks in the water and keeps the water in the textile structure. And even on an elastic fiber that has been elongated by 300%, we still maintain these very good hydrophobic properties. When it comes to the comparison, we were immersing it into water for 10 minutes and then removing it, measuring the weight gain and then the drying properties. The plasma coating dries quickly. The fluorocarbon C6 is comparable, but other PFAS-free substitutes we were looking at, they perform less good. And if it comes after 5 times washing, C6 is still acceptable. However, the plasma coating largely maintains good properties and other, so C0 chemistry shows a lower performance. So indeed, we have a very good water repellency. It's related to a very high capillary depression, resulting fast drying, which is even outperforming PFAS. However, when it comes to oil stain repellency, this is wetting. So this is a very nice approach, however, only for hydrophobicity. And I'd like to stress this is nanometer thick coating. So we are using 100 to about 1,000 times lower amount of material than with the wet chemical approach. Let's look at a few other possibilities. So this is was so far simply, let's say, a replacement by a hydrophobic coating to improve the effects. We are looking at catalytic active surfaces. They can be also very, very thin, deposited by plasma. It's a silver doped titanium oxide, and in interaction with water and oxygen, it's producing reactive oxygen species. And we can maintain this catalytic effect by putting a very thin hydrophobic plasma layer on top. And like this, we can combine repellency with oxidative destruction of organics, but also bacteria, which is currently our main interest. When you look at bacteria here with the 5 nanometer thick hydrophobic coating, we still see a good effect here on some bacteria, a little bit reduced for some others for the hydrophobic. And we have more nanoporous coatings. That means better access of water to the catalytic active surface. we maintain very good oxidative destruction and antimicrobial effects. And that happens within minutes. It's not that this takes a long time. That would be one chance somehow to combine repellent effects with an active surfaces. Typical approach, when you look at literature, they consider nanostructured surfaces. The idea is that you have air trapping and therefore get a higher repellency. On PDMS, that can be done by laser texturing, and indeed it's shown you have very high water repellency, but also some oil repellency. Also, you repel a few other substances, not everything, but it already looks promising. However, those surfaces tend to be abraded, which is a remaining issue. You have limited durability, and then whenever you have a situation, if you apply a force, you have air displacement, you're also losing these beneficial properties. And when you have some wear, you have a situation where you then also lose the oil repellent properties readily again. There's been some other ways to deal with it when you have a structured, textured surface which is hydrophilic but slightly oleophobic. And then you immerse everything in water. Then in water, so underwater, you get super oleophobic surfaces. That can be done with different structures. Again, also in PDMS or with the hydrophilic properties. That has been done in a plasma treated as well. So that could be a way for some applications, but it shows maybe some potential to look at liquid-infused surfaces. Also here you are using a porous textured surface. Nowadays, it's still PFAS that are used to be immersed into the structures, and then you have highly repellent properties. However, to replace PFAS, you can immerse other substances. We could show that we have hydrophilic substances immersed in a nanoporous plasma polymer, which shows a much higher durability. You have less depletion. And for example, here shown with the lubricating silicone oil that you have permanent low friction properties. And now from this, one might start to infuse with other liquids to go more towards oil repellency. So this is just a few ideas I like to give where it might go. Definitely there's research needed. And with this, let's see what we can discuss after my talk. I'd like to conclude. So there are some options to replace polyfluoroalkyl substances, but also limitations, since they indeed have very unique characteristics. It's not only low surface energy, it's also what it's called fatness. So they take a lot of space and have a low interaction with substances by this effect. If you like to replace them with siloxane silanes, typically much thicker coatings are required. Issues of degradation durability should be considered. A way we are following, therefore, is to introduce ultra-thin coatings, nanometers with terminal methyl groups fixed on a durable siloxane chemistry. That works very well for hydrophobic surfaces. Currently, we're working on this, but definitely that will take a few years. Currently not for oil repellency. Therefore, we need to do further work. We are open for partners. Of course, we need funding, but we have a dry and sustainable approach with the plasma technology. With this, I'd like to thank all my colleagues and Empa who did most of the work, of course, and I thank you for your attention.
Thank you very much, Dirk. It was an excellent overview of the basics of what challenges we face in developing PFAS alternative and what we are doing at Empa. So thank you very much. I do see a few questions, so I'm gonna go through them one by one. I start with the written ones on the chat. The first question is from Nelson. Will the presentations be made available? I believe we are recording this presentation, so you could access it through the community's platform where the presentation or the video will be there. I'm not sure if we have requested the speakers to provide us with their slides. So I'm not sure. Maria, do we have permission to share the slides?
I'm not aware of that at the moment. We can talk about that later with the speakers and see if they'll give permissions to use their slides. If they do, I will also upload that to the communities.
Okay, I would suggest that if you are interested, you could directly contact individual speaker, and hopefully they would be able to address your needs. The second question is from Mustafa Arifoglu, and his question is, does the deposited thin film affect fabric breathability?
So, quick answer, no. The reason is simply low amount of material deposited in the nanometer range. You don't interfere with textile properties other than friction or really surface related properties, but not touch, not pressability.
So Dirk, I actually had a similar question. In the beginning, you showed some patterns where very thick coatings, micron level coatings were used, which offer similar efficacy compared to the thin coatings you are making at Empa. So what is the reason behind that, I would say? Why Empa coatings are much as good as the thick coatings?
There's still a difference, to be honest here. We do very thin coatings, so they are smooth, flat, yeah? They don't have this hierarchical structure. And one way to approach or to get a higher repellency is by introducing centrimere structures, hierarchical structures. You have air trapment, and therefore you get, for some applications, much better effects. It's always about the application finally. We will not find one substance replacing PFAS for all applications. The way to go will be that you need to know the requirements for your applications. For some, water repellency, fast drying might be sufficient. Then it's good to do this with a very thin coating. If you have other requirements that will be not sufficient, our approach, yeah, then you might need to introduce thicker coatings, these dendritic structures, hierarchical structures, and so on. But they again might fail in some situations. So it's a tricky situation. You will not have one solution for replacing PFAS in all these application fields where they are now in. You need to find one solution for every field, for every application. That's my opinion.
Very good. So the next question is from Renuka. Where question is, well, it's a good presentation. Has the water repellent coating using plasma applied on cotton substrate?
Yeah, so we started to work with synthetic fibers, including elastic fibers. Meanwhile, we applied them to different materials, and you can deposit it on all kinds of materials, also on cotton. Yeah, again, you need to check what are the requirements. So far, it looks as if we get pretty good properties on cotton as well. One requirement, since we need this chemical bond directly to the polymer surface, is that we have clean fibers. Yeah, as long as there are still manufacturing residuals, any kind of osimage, avivage, whatever you name it, still on, we need to have first the cleaning step. So the best is always when fibers or textiles are provided with the lowest amount of residual oils or any other substances at the surface.
Thank you. So there is this comment from Ram. He says, please request lies as it is knowledge sharing. So probably we will speak about it later with the speakers. Hopefully they will share the slides. The next question is from Paul Torres. The question is cost effectiveness using ultra thin siloxane films. So they want to know how expensive this coating is. Yeah.
Yeah. So once if you have a running process, the costs are low. So low amount of materials needed and also from energy. And so it's a dry process. That is the good side. Yeah. First, you need to have an investment. And currently we have a pilot scale reactor. We're scaling it up, but it needs to get even larger. Yeah, though there is still some work to do. Once if you have set up large equipment with high throughput, yes, then you definitely meet all economic aspects. That has been shown in other fields. Is it coating on architectural classes, coatings on films, semiconductor industry? So you lower the costs when you go large.
And the fact that all chemicals, the precursors are not expensive at all, huh? So that helps.
Yes, I mean, that is an important aspect. You need to have a proper selection there. Also concerning maybe coming up issues with some chemicals, but you have the freedom, you can mix chemicals, so you can always start with non-toxic, non-hazardous chemicals, cheap chemicals, and with thin coatings, so the running costs are low, but I have to admit that the investment is something definitely to be considered, yes.
Yeah. The next question is from Ben Watmuth, and the question is there any benefit to plasma treating the surface of an untreated substrate and then using the pad bath method to apply coating?
Yeah, that is indeed a good question. I was not commenting on this here, but indeed we will maybe then see in the next talk. The industry does huge progress also in replacing PFAS with solution coatings, and the plasma activation might still help depending on the substrate, the requirements, durability, and so on. That could indeed be also a good way somehow to combine the best of two worlds. Yeah.
Okay. The next question is from Lamberti de. Thank you for your presentation. When durability is discussed, is it home laundry? Has laundering testing been done on ultra-thin plasma coating?
Yeah, so what I was showing here was an accelerated laundering or washing test. We use typical soap or surfactants in water at 60 degrees with polymer balls. And then everything is, yeah, it's washed.
Dirk, I think it's a AATCC standard we use.
Yeah, probably. Since I never have done it myself, I just try to explain.
I know it's.
But I'm told it's comparable to kind of an industrial laundering step. We did it only 5 times. For us, it's a big effort to do this. Yeah, but this is what I've shown. It looks pretty good. For other coatings, other applications, we went up to 50 times and it's still good. So from this side, I really see the advantage of this, the chemical binding of these very thin coatings directly on the polymer.
Okay. The next question is from Kasao Gebeyu, and he is talking about your opinion on the scalability issues of plasma technology for textiles. The challenges, I believe.
Yeah, absolutely. This is challenging. Luckily, we now have 20 years experience also with building plasma reactors. We do this together with industries, and these are new machines, new concepts that we need. And we are in the phase of scaling. So as mentioned, we have a pilot scale reactor. In principle, we could go already up to 1,000 meters per minute to meet the coating thickness and all requirements. But the handling of the fiber yarn at this speed still a little bit challenged. So that means we need to parallelize it. So we have to have the treatment of many, many yarns at once. And this is now where we are going, what we need to show next.
Okay, so I'll take one more question. The question is, does plasma treatment impact physical properties due to presence of silicon?
That is also a good question. So there are different aspects. So the idea is, as I mentioned, plasma to do it at low temperature. Then typically we maintain mechanical properties. There is no loss. When it comes to the coating, as I briefly mentioned, we might change friction properties. Depending on the textile processes you are doing afterwards, you can apply also a weaving oil or any other means you need for textile processing, but it might not even be required in every case. So then, of course, you need to look at the properties of your fiber material or your yarn material. Yes.
Okay, so I will be considerate. I will ask two more questions very quickly. Do these plasma treatment have positive or negative? Do they have positive or negative effect on dyeing later on? And the other question is, can this technology be used in extrusion of yarns? So is this technology compatible in extrusion of yarns? But I think you have a very good answer for that. I know. Yeah.
They are, first of all, very good questions. Let's see if I have find a good answer. So what we are aiming for is to protect the fiber by this thin coating. We really aim in wrapping it and have coating everywhere. Of course, this is interfering with the dyeing process, at least when you consider standard dyeing processes. Yeah. So currently recommend dyeing first, then our treatment. Yeah. If you're willing to adjust dyeing procedure, there I see chances because the coating is thin, but you would need to look at the interaction by dyeing. Simply using high temperatures and these rather harsh conditions that are typically used in dyeing, that is not a good way to do it. And the other, to apply it directly after extrusion, it's quite interesting. Yeah, I will now not comment too much on it, but yeah, some ideas in this direction we have. But coding is still challenging because just look at the speeds you have by melt fiber spinning and all these processes. Yeah, but it's something to be followed up. Yeah. Mm-hmm.
Okay, but Dirk, we do have the technology where we can process yarns or fibers directly.
Yes.
Okay,
absolutely.
That's what I want to
That is one strong aspect of our lab, advanced fibers, that we dealing with all these different processing steps, fibers, extrusion, compounding, melt spinning, modifying, additives, and finishings, including plasma and also other techniques, dip coating and everything. We can do everything on a fiber level and combine it.
Okay, so Dirk, thank you very much for your nice presentation and willing to answer all the questions. We will now move to the next speaker. Next speaker is Luka Kovacevic. He's from industry and he's going to talk about some practical solutions they have developed in Rudolf Chemie. So please, Lukas, floor is yours.
Okay, thank you for the introduction, for the kind. I'm uploading the slides. Okay, here we go. Bionic Finish Eco. So that's the name of the brand of our fluorine-free water repellent technology. And here I'm going to give you a quick review how we started, where we are applying this technology today, what our customers are doing, and I'm also going to show you what the recent developments are, what the current challenges are with fluorine-free technology. A little bit for orientation, here's a quick outline. I'm going to spend a few words on our company, Rudolf. Then I'm going to say something about the chemical background of our fluorine-free technology, Bionic Finish Eco. Then we're going to have a look at the scope and applications of Ruco Dry Eco Plus, which is our best-selling product from the Bionic Finish Eco family. We're going to have a quick talk and a quick look at advanced durability extenders. This is a particular class of chemistry that is there for providing durability to water repellent finishes. Then we're going to have a look at PFAS-free solutions beyond the traditional pad dry cure finishing methods. There are some interesting innovations and also some alternative application methods that you may not know of. We're gonna discuss them as well. And lastly, we will finish with the current challenges of water repellent finishes that we see with our customer base. And I'm also going to show a glimpse of what we are working on right now. Okay. Rudolf, who are we? This is the wrong slide. So we were established in 1922, so we've been around for more than 100 years. We are still privately owned by the Schumann family in its fourth generation. Over the years, we have become a global company with almost 2,000 people worldwide. We are located in all textile markets around the globe. We have many production sites, although the main production hub is a little bit south of Munich in Germany, where most of our sophisticated chemistry comes from, and we are approaching 400 million in turnover. At Rudolf, hold on a second. At Rudolf, we don't only provide textile chemicals. Over the last 20 years, we have also developed other business areas, for example, construction chemicals, textile care chemicals, and lately we've also been exploring ingredients for car care applications. Rudolf does not only sell textile chemicals, we also offer our customers services. For example, you can send us untreated textile material and we can have a look at it. We can work on the recipe with the desired effect, with a desired product that you want to have on. We have a vast set of tests and standards that we can perform at Rudolf. We also provide analytical services and so on and so on. Okay, Bionic Finish Eco, that's the name of our fluorine-free technology. So what is it? Most of you that have maybe come across Rudolf as a manufacturer of fluorine-free water repellents might have heard the word dendrimers. Dendrimers is the base of our technology, although most of it is a buzzword because it does not describe a chemical class. It is a structural element, and in fact, our chemistry is based on a highly modified polyurethane technology that makes sophisticated structures. So these tree-like polymers, that is where the terminology dendrimers comes. In Greek, it means tree, and these little polymers are fascinating because they make large surfaces. And that means by using little amounts of chemistry, you can create great and exceptional performance and effects. And by using little amounts of chemistry on the fabric, you only impact durability, breathability, fabric handle, optical appearance minimally. This technology was patented in 2003 for the first time, with some patents to follow that. You see, we've been in that business with fluorine-free finishes for a while now. Okay, bionic finish is, of course, compliant with the major substance restriction substance lists, such as Oeko-Tex, bluesign, GOTS, ZDHC. And needless to say that our chemistry is not only free of PFAS, but also we do not work with adsorbable organic halides. That includes PVCs. We also don't work with, or our compounds don't include siloxane cycles. Dirk has previously said that they are facing regulatory activities. We don't use APOs as emulsifier or surfactants in our products, and our products are also free of heavy metals. PFAS, I'm just going to give you a little update on regulatory activities here. Due to their very persistent properties, and that's why they're called forever chemicals, the EU and the US, they are going to phase them out quite soon. Only, a couple of weeks ago, a restriction ban for PFHXA, which is a synonym for the C6 chemical, which is used as water repellent agents in textiles. That has been, the restriction ban for that has been adopted by the European Union. There is a transition time until the complete phase out until 2026, 27. And there are only a little number of exemptions. For example, personal protective equipment, medical devices, and construction textiles. In the US, we have a similar phase-out program, or let's say a regulation program, the PFAS roadmap. Only recently, the EPA has designated PFOA, PFOS, the C8 compounds, as hazardous substances under circular. EPA has also introduced national drinking water standards for PFAS, putting pressure on public water suppliers and making it hard for everyone to work with PFAS. Lastly, the textile certification systems, Oeko-Tex, ZDHC, bluesign, they have all banned PFAS from textile from this year. Okay, Dry Eco Plus, our best-selling water repellent product. What is it? Well, it's a dendrimer-based polymer technology. It works on synthetics as well as on cellulosic and natural fibers. It is definitely the most versatile product, and it offers the best initial and most durable water repellent performance. Particular highlights of this fabric finish is, compared to alternative technologies, that it provides a really soft fabric handle, and due to the sturdy polyurethane polymers, it also offers some excellent abrasion resistance. Fluorine-free Eco Plus was first introduced and is still primarily used for the water repellent finishing of sports, outdoor, and fashion apparel of synthetic materials. However, it also works on cellulosics, which is shown here. We can get on synthetics and cellulosic a spray rating of 100 without any problems. And most of our customers are interested in the spray rating of Eco Plus finished textiles, but they also care a lot about the durability. And in best case scenarios, we can achieve durability of the finish up to 30 washes. Okay. Some customers want to have a more, I'd say, in-depth look on performance, and this is when the Bundesmann test comes into play. Here you have the fabric samples attached to these chambers, the water drops fall from a greater height. Okay, so you have more impact on the fabric samples. There's a rotating metal frame or crossbar putting mechanical stress on the treated textiles from underneath, and you can also measure the penetration of the water that goes through the fabric. So you get three different performance parameters. One is repellency, similar to the spray test before, but you can also measure water penetration and water absorption of the fabric itself. Okay. And in this chart, in these charts here, you can see that EcoPlus finish can achieve almost similar performance figures as a C6 finish. The shoe industry has started looking quite late into fluorine-free water repellent products for various shoe materials. With shoe material applications, one of the most employed performance test is the anti-wicking test or Gore test that you can see on the right-hand side. In this standard, treated fabric is immersed in aqueous blue solution, and the water must not rise above 10 millimeters within 2 or 4 hours. Again, you can see that our EcoPlus can achieve same performance as a C6 finish. It has to be said, however, that to be comparable with a C6 finish, all the untreated material before finishing have to be free of residual surfactants. Lately, some customers producing reusable medical gowns and drapes have started looking into applying EcoPlus on medical fabric. With medical drapes and gowns, the key performance criteria is the hydrostatic head, and you can see that even here, EcoPlus is not too far from a C6 finish and can sustain a sufficient number of disinfected wash cycles at higher temperatures. Yeah. We now also have a significant number of customers who are producing personal protective equipment with chemical protection using EcoPlus. Surely solvent-like test chemicals like xylene or butanol cannot be repelled by this fluorine-free chemistry, but you can see that, for example, on aramid, sulfuric acid concentrated or concentrated sodium hydroxide solution can be repelled quite effectively according to the chemical repellency standard, and this applies for even a high number of industrial washes. After 50 washes here, you can see that we are still have a repellency factor of 97, 98 degrees. On polycotton, the durability is a bit lower, but still above the 95% range in this case. Furniture producers have started using EcoPlus as a protective treatment for upholstery and other home textiles. With upholstery, this kind of customer base is particularly interested in the strong resistance of EcoPlus finishes towards abrasion compared to, and which is superior, or at least we find it superior to some alternative non-fluorinated water repellent agents out there. And another aspect that is tested by these furniture or home textile producers is the stain repellent properties of EcoPlus. In this image here, you can show that EcoPlus is not only able to repel water, but an array of different aqueous stains, even fat-containing liquids like milk, or alcohol-containing liquids like red wine. And this repellency applies also for even after a high number of home washes. Okay, let's quickly speak about durability extenders because they are also quite important for providing durability of water repellent finishes to the fabric, to the finish. The chemical class of durability extenders is also called blocked polyisocyanates. How do they work? Well, we have these polymeric isocyanates, which are so reactive, the isocyanate group, abbreviated here as with NCO, is so reactive that it has to be protected by blocking groups in the first place. And until recently, the main blocking group used for this type of chemistry has been MECO, or also known as 2-butanoxime, but that has recently become or changed in classification from H351 to H315. These compounds have now become hazardous goods. Our customers are moving away from that. In fact, BlueSign has imposed a ban of all MECO-based chemicals, and now the alternative blocking agent for this product group is DMP. DMP is also a little bit controversial because it's mutagen, so it's also a CMR substance. CMR stands for cancerogen, mutagen, reprotoxic. So we have our customer base is now moving away from these MECO-based cross-linkers to these DMP blocked polyisocyanates as the new standard. However, we have already prepared for the future, and we have also cross-linking additives with that are DMP and MECO-free, that are blocked with a relatively harmless amine, and this is something that we offer already. We are also exploring new cross-linking technologies that work for synthetics and cellulosics. We have the Rucolink X and B, which is a little bit different in its with its functional groups. We don't have any isocyanates anymore. It's a technology that is completely emissions free, so no blocking groups involved. When you're not working with blocking groups, that means you don't have to deblock them, so you have in the recipe a cross-linking additive that also works at low curing conditions, which is quite interesting for some applications. Okay, let's have a look at some applications that we have turned into non-fluorinated applications over the last few years that are beyond the typical pad dry cure application method. I have to say most of our products have been designed for the pad application. However, we are now also exploring new ways of applying water repellent agents. One is the industrial spray application by the Baldwin or the Weco spray type machine. Here you have huge advantages in terms of saving energy, chemicals, and water, because the pickup, fabric pickup with these spray applications is a lot lower compared to the pad application. So here you only have 15 to 30% pickup of the finishing lacquer compared to 60 to 80 or sometimes 50 to 80 on a regular pad application. So that means your spray solutions have to be a lot more concentrated. So that also means these you have less water in your spray solution, and in the end you have to evaporate less water from the finish after the finishing. That means you need to apply less energy. At the same time, these systems also create a lot less waste, chemical waste, and what is also charming about this application technique is that with these spray applications, you can apply contactless, and you can also apply single-sided. Okay, so that means only at the side where you want the chemical to make effects. Reproofing and refreshing the properties of personal protective equipment, workwear, and medical textiles in industrial laundries has also been one of our business in the aftercare market. Until recently, These reproofing services have been conducted with PFAS, C6-based water repellent agents exclusively. Only now our customer base has started looking into products like PFAS-free Ruco 1510 and is more and more employed in these industrial laundries. Rudolf also specializes in creating solvent-based water repellents that are either used for consumer aerosol spray containers, or there are some sophisticated industrial applications that use solvent-based water repellent agents. The charming aspect of solvent-based water repellents is that you have a targeted application, you have a quick and uniform penetration and coverage of the water repellent spray solutions. You have quick drying, and typically you don't have to cure the water repellent finishes to develop the performance. These are air cure products typically. So for consumer applications, we have two different solvent-based products. For industrial applications, we have another two with a bit of a with higher boiling, with solvents that have a higher boiling points to make the industrial application where they use higher amounts of product a bit more safe. More and more popular are becoming these aqueous reproofing sprays for aftercare solutions because you don't have to deal with smelly or flammable solvents. The application is more safe. However, the disadvantages is that it is quite difficult to get a good and even penetration of fabrics that have been industrially finished before and that now have to be reproved. But we have products for that. Ruco 1419 is one example that can be applied via this trigger spray device or application. Last consumer care application is this wash-in application, which is quite popular and that can be applied via a softener compartment. The good thing about that is you get your hands, you don't get your hands dirty, so no chemicals on your hands. You just apply it to the softener compartment and you apply it in the last rinse. It's a very clean and effortless, easy to do application. What sounds quite easy to do is, in fact, well, our experience is that a lot of things can go wrong, starting from putting detergent into the washing machine at the same time, which will, of course, impair the water repellent performance at the end, and other things can also go wrong. Right, last chapter, current challenges of PFAS-free finishes, and I'm going to show you some innovations, some solutions that we are working on. So for the growing number of customers with more sophisticated textile applications, we have expanded our product portfolio a little bit. So we're not selling Eco Plus only anymore. So we now have also products that have a higher resistance to dry cleaning. We have products that tackle the chalk mark issues that I'm going to speak about in a minute. We have products that have less impact on flame retardant properties of a textile application compared to Eco Plus. We also have non-ionic water repellent agents that can be combined with anionic auxiliaries, for example, binders, biocides. But our feedback from the market, where the biggest challenges are, I'm going to show you on the next slides here. Chalk marking, also known as Markov. This is the number one issue that our customers are facing. This is the the unsightly white or bright marks you can create on a treated fabric when you scratch with your fingernails over it. Here, for example, you see these marks, okay? This mark-off has also been known with fluorine-free based finishes, but as fluorine-free water repellents are less powerful, you have to use more fluorine-free water repellent agents to create comparable water repellent performance, and more chemistry on the fabric is simply more visible. Not in every case, but it happens here and there on particular colors, not the very dark ones, not the very bright ones. It is most often seen on the middle tones, particularly synthetics. There are ways to overcome this problem by less durable water repellent dosage or calendering after finishing, which is more costly at the same time and is an extra step. However, it usually does not solve these problems completely. Second biggest problem is seam slippage, which is facilitated by, let's have a look whether I can, cursor, now it works. Yeah, there we have a video of it, which is facilitated by these water repellent agents. The polymers simply facilitate the gliding properties of the fibers, so the fibers themselves become a little bit more mobile when tear is applied. And of course, this is not a desired feature, that the rope, the seam opening is more facilitated. Fabrics can lose shape, and water can also penetrate through the seam holes. This is also something that we are trying to improve. Lamination properties is also something that our customers are worried about. Here's a video from a visit in a Chinese mill where they were looking at lamination strengths. You can see that there's this fabric where tape has been attached to. Then they have this handheld, how would I call it? A force measurement device, which can pull off the tape, and by pulling off, you can read the force that is needed to pull off that tape. And yeah, a number of customers are currently looking into enhancing the line dry properties of water repellent finishes. That means that after laundering water repellent textile articles, you can just dry them at ambient temperature, and the water repellent performance will come back as in the beginning. That's unfortunately not how it works today, but this is something that people are looking at. Why do we actually have to reactivate the water repellent performance by heat after laundering? Well, the thing is that after the finishing on the fabric surface, you have the polymers in an ideal crystallized way. You see those side chain modifications of the polymer. They are pointing away from the fabric, making a nice structure. After the laundering process, this polymer gets disorientated, loses not only structure, but also the repellent function. And this is why you have to apply heat by tumbling, by ironing, and by that you can melt these polymers, make them a bit more mobile, and these side modifications can realign, crystallize, and develop the initial performance again. So for tackling the mark-off issues, we issued we launched a product called Rukodry Eco PSS a while ago. It contains some specialized and modified silicons that is a polymer that can level out these chalk marks or mark-offs, and at the same time as it is based on silicons, it can provide exceptional softness. At the same time, we also get enhanced laundry air dry performance. However, it is a little bit weaker in terms of performance than our traditional Eco Plus. But as you can see here, the mark-off can get reduced dramatically. Okay. What we are working at the moment is a combination of this Eco PSS. So that product that is has been created against chalk marks, and we are looking for a solution that at the same time provides water repellent performance of an Eco Plus. Here you can see in this graph, so spray test of Eco Plus finishes yields a 100, no problems. Our Eco PSS can achieve a 90 only, sometimes even lower on particular fibers. It has, so these are spray test figures after line drying. So you can see that after a number of washes, the Eco Plus loses performance after line drying quite quickly. Mark-off is relatively strong. Eco PSS starts off with a lower initial spray, but can keep a moderate water repellency after line drying over a higher number of washes. And here we have something that I call Formulation X. It's not a product yet, but we can improve the initial spray to a level of Eco Plus, and we can also improve the line dry water repellent performance. You can see that even after the 5th wash, you can have a grade of 80 in spray testing. Mark-off is really good. This is something that we are working right now. We have also tested lamination strength. Some people in the field are worried about silicons that are employed for making these water repellent agents can negatively affect lamination properties. In this trials here, we tested the lamination strength of Eco Plus, Eco PSS, and the new formulation. We did that a little bit more sophisticated than the Chinese worker in the mill. We also checked for seam slippage, and we're measuring seam opening by this method I showed in the video. Here you can see that compared to Eco Plus, we can also reduce the seam opening with these new formulations. Okay, so this was my last slide, and now I'm happy to receive questions.
Thank you, Lucas. We have time for some questions. The first question is from Nilay Desai. He's asking, what's your recommendation or recommended temperature on single phase tenter pass?
Single phase, sorry, say it again, please. Phase.
What's your recommendation temperature on single phase tenter pass?
Tenter pass. Well, typically the applications are run. Well, it depends. When you use a crosslinker for achieving highest durability of the water repellent finishes, you will have to use a cross-linking additive. A cross-linking additive is not always needed, but when you have to use a cross-linking additive, you need the curing temperatures that will deblock or activate the cross-linking agent, and that happens at 170 to 170 degrees Celsius. Someone will have to convert this to Fahrenheit. And for synthetics, you will have to hold this for about 60 seconds. If you have a cellulosic fiber, you will probably need twice the time, yeah, a longer time at least.
Okay, so the same gentleman has a few questions. The first question is, does medical gown pass 2 levels test, AATCC 42, AATCC 127?
We have done trials. It's a good question. It's a good question. I think last time we looked at these test standards was during the COVID time. To be honest with you, I would have to dig out the numbers, but I am positive that we could achieve the requirement at least on synthetics. There are, however, some fabrics that involve polycotton, where it is definitely more difficult to use a PFAS-free system.
Okay, so subsequent questions are, what's your suggestion on low pickup fabric with low GSM? Any wetter can help without impacting performance level.
Yes, we have a specialized wetting aid. It is called Ruko Wet RPS. It is based on some glycols that help some wetting already. It also has some specialized surfactants that do not impair or the subsequent hydrophobic properties that much. Of course, you cannot use it in excess amounts, but it can definitely improve the penetration, particularly when it comes to fibers such as polypropylene that is known for really low pickup.
Yeah. Do you have any data on aqueous-borne stain release data? As you said on medical gown, any data on blood stains?
Oh, that's a good question. Honestly, we have not used blood or blood surrogate, test material for any of our tests so far. So I don't really have an opinion on that. But it would be interesting. So synthetic blood is not something that we have employed before.
And the fact that you have an aqueous solution, I don't think there will be any difference in performance, I would say. I'm not sure if blood is any different, but that's my guess.
Well, it definitely has a lower surface tension, so it is difficult maybe to repel. Definitely more difficult to repel than water.
Okay, good. Then there is a question from Dina. Thanks for your presentation. The wash care instructions should be used for the treated fabric. Please advise with many thanks.
Sorry, what is the question here?
The wash care instruction. What kind of wash care instructions is provided with, is recommended for a treated fabric?
Water treated fabric. Okay, so yeah, I think that it also applies to some consumer articles that are washed in the home laundry. So most importantly is, well, what we typically recommend is to use a mild detergent. These mild detergents typically consist of only anionic surfactants that are easily rinsed out of the fabric. An extra rinse is typically also recommended to really get all residual surfactants out of the fabric. I also recommend our customers to hang dry their garments first until they're completely dry, and then they can apply heat by tumbling or ironing. Sometimes when you put wet clothes into the tumbler, you sometimes you cannot get the full performance back or any performance at all because you have not finished the drying of the fabric. So it is important that the fabric is dry completely before you reactivate by additional heat treatment.
Okay, the question from Clark, Jared. Have you tested repellency using Bundesmann before and after washing for some of these products?
Yes, we have. Yes, we have.
Okay.
What is interesting, typically after the first wash, the Bundesmann values definitely increase and get better. This is due to the emulsifiers that you have on the fabric that you also bring onto the fiber with your finish, okay? Because you have those emulsifiers to get those polymers processable. You have to make a stable formulation. And to make it a processable product. That's why you have emulsifiers in the product. And these are, of course, also on the fabric when you finish it initially. And once you have done a Bundesmann test, these emulsifiers are washed out, and then the performance gets better until after a number of wash cycles, the Bundesmann values drop again.
Next question from Alex Saputro. The question is for non-textile materials such as silicone items, for example, swim cap, any possibility for PFAS contamination during manufacturing process?
Well, can you repeat that material again?
So for non-textile materials such as silicone items, for example, swim caps, any possibility for PFAS contamination during manufacturing process?
I honestly have no opinion on that.
Okay, even I'm confused with this question. I'm not sure why is PFAS coming here. Do they already contain PFAS coating? Then why do you need to do your coating? So anyway, so maybe he can clarify the question. So next question is Kasov Gebehu, if I pronounce this correctly. Your comment on uniformity of finish application via spraying over the traditionally pad dry cure application.
Okay.
So would you like to comment? Like, I think you did explain it very well, but maybe you can summarize it.
I was showing 3 different spray application techniques. So first, the industrially used Baldwin or Waco machines that are just an alternative to the traditional pad dry cure application. So there you don't, well, of course the penetration can sometimes be an issue. Again, you can use wetting aids to improve penetration. Of course, not every fabric material is suitable when you are addressing the solvent-based wash repellent agents. I can say that the solvent type sprays, they are the best that you can have in terms of penetration, because the surface tension of solvent-based solutions is so small that the spray solutions, they spread quickly, they wet quickly, they penetrate very efficiently. In fact, it's actually best in terms of uniform coverage that you can have. If it was not for the smell, if it was not for the flammability and for the safeness of the application. Yeah.
Okay. Other question from the gentleman is, do dendrimers reduce surface energy, or do they increase surface roughness? Well, the question is regarding the mechanism, huh? So what is the mechanism behind?
So these specialized polyurethanes that we call dendrimers, they have long alkyl chains attached to the polymer backbone, so the polyurethane backbone, and these alkyl chains, they definitely reduce the surface tension, and that's why they can be used as water repellent ingredients and substances.
Okay. One final question from audience. How is the color or shade of the fabric impacted, of a dyed fabric, I would say, after your treatment?
Yeah, so it is always affected. So this is something that we are, to be honest with you, we are exploring that right now. So far, we have always said, yeah, it does affect the color to some extent. However, from our customer base, I've heard that among alternative technologies, our dendrimer-based products affect color change quite minimal. In what direction the color goes, this is one point that we are exploring right now.
Okay. Actually, I had a few questions, but I would ask you this very basic question. What is the mechanism behind the durability? Is it because the dendrimers react to the substrate, or they network on the surface and they become insoluble in water? So what exactly is the mechanism there? Or it is a combination of both?
There are different mechanisms that add to the durability of the polymers. So one is the polymers themselves. They are quite insoluble. The goal is always to produce really large molecules, because larger molecules, polymers, they are even less soluble to aqueous systems. Then you have the cross-linking additives that can, at least on cellulosic fibers, they can really cross-link chemically the polymers to the hydroxyl groups of natural fibers. When you have reactive cross-linking anchor points in the polymers, what we have on synthetic fibers, where you don't have anchoring groups on the substrate, you are forming even larger polymers by cross-linking the polymers to each other, and by that they get even more insoluble.
Okay, it's actually a final question which I forgot to ask. It was actually addressed to the previous speaker, but it's a general question. Many of these textiles, treated textiles, are also used by firefighters. Do you think the fire performance of these textiles could be affected by your treatment? So if you could answer this question, then maybe Dirk could follow with his answer, I would say.
I will say yes. I will say yes. Our experience is every kind of chemical that you put on your fiber will always affect flame retardant properties negatively, unless it is really an FR agent, that is a particular class of its own. Yeah, because typically all these polymers that you put on, they are organic, and organic material just burns well.
Okay, thank you, Luka. Dirk, do you want to comment on that?
I can comment. That's an aspect we were not yet looking at, so we should discuss. Okay. My answer for now would be, of course, we add material, but since it's 0.1 weight% or below, it doesn't even disturb by recycling the fibers. It should not affect flame retardant properties.
Okay, I could actually add to this answer. I know silicones which we apply, they could have beneficial effect, but also could have detrimental effect depending on the type of substrate. So if it is a cellulose, silicone definitely has a beneficial effect. So it also adds to the charring and acts as a barrier. But if it comes to synthetic polymers, silicone acts as a kind of a scaffold and may accelerate the flaming propensity of these textiles. So saying that, I haven't done the test, but this is something from my common knowledge, I would say. But I hope I have answered the question of this audience. So I don't see any more questions, and I do not have any more questions from my side. So I would like to thank, I would say, both the speakers for this very interesting talks. I really enjoyed. I learned a lot. I hope the audience learned a lot, and they had actually quite a good participation. They asked a lot of questions. I think we have learned a lot, and I thank all the audience for their participation as well. And I thank AATCC as well for organizing such events and trying to do the knowledge transfer back and forth, industry and academia, vice versa. So again, I thank all of you, and hopefully we can keep these kind of discussions going on. I will speak to the speakers and try to get their presentations if we can share, but I'll come back to you guys later. So thank you again, and have a nice morning for you guys, most of you, and a nice evening to our European, speaker and myself. Thank you very much. Bye-bye.
Thanks. Bye.